If you think I should contact any authorities, let me know. I'll try to save the dead person and just leave that for now. Alright, so what I want to do is, I think I've been talking for several weeks about Weierstrass's no differentiable function. Let me at least state it. So, Weierstrass's continuous but nowhere differentiable function. Can someone give me an example of a function that is nowhere differentiable?
Indicator function Q?
Yeah, take the indicator function of the rational numbers. It's 1 on rationals, 0 on irrationals. So that function will be differentiable nowhere. In fact, it's continuous nowhere. And if you're not continuous, you can't be differentiable. What's amazing about Weierstrass's example is that it's continuous everywhere. And so here's a great example. And this may be a slight modification of the example he came up with, but it's essentially in the same spirit. So let's let Fa of x be the sum, n goes from, say, 0 to infinity of a to the n cosine of 2 to the n times 2 pi x. And we'll assume 1/2 is less than a is less than 1. So if you look at this, essentially because I have cosines, my Fourier coefficients are only occurring really when I'm at a power of 2. So I have these extremely long deserts that are constantly growing between non-zero Fourier coefficients. What's the derivative? Or what would you like to guess? If nobody speaks up, the physicists have to answer. What's the derivative? Okay, this is the continuous but nowhere differentiable function, so the derivative will not exist. But if you had to guess, what would you guess?
Something with signs.
Okay, be a little bit more specific. What else?
Pull up 2 to the n 2 pi, so a to the n 2 to the n 2 pi.
Excellent.
With a minus sign.
You don't worry about the fact that you're interchanging orders of operation. You just keep going, and you'll get 2a to the n times 2 pi, and the derivative of cosine is? Negative sign. And the way I remember it is, there's a mnemonic. You have to remember where the minus sign goes. It's minus sign. So 2 pi sine 2 to the n times 2 pi x. Converge or not? So does this converge? What do you think?
No.
No, why not?
Because 2a is greater than 1.
Yeah, because 2a is greater than 1. Why don't I let over here a be equal to 5 and just have even worse failure here? Why did I truncate a and say a was less than 1?
Would that give you problems with continuity? If you
Yeah, that'll give me problems with continuity. Right? I need a to be less than 1 in order for this sum to converge. So a being less than 1 allows this sum to converge. A being greater than 1/2 allows this sum to diverge. So if I were to try to differentiate this term by term, it would not work. Okay. Any questions on Weierstrass's continuous but nowhere differentiable function?
Can we see a picture of it?
I'm sorry?
Can we see it? Like,
I'll post a picture of it. You can actually...
I mean, I've seen it. I think I've seen it already. I just...
Yeah, I'll post a picture of this. It's not that hard to plot this in Mathematica. Because the thing is, the extra values of n really don't change the function by that much. I mean, when n is 10, you get, if a is around 1/2, you get a 1 over 1,000. Then when a is 20, it's 1 over 100,000. Or is it 1 over, sorry, million? So very quickly, the contributions from the higher n are insignificant. But they will affect, thank you. But they will affect whether or not it's differentiable. So that's the thing, is you can affect continuity with very small bumps in a negligible way, but those bumps will have huge impact on the differentiability. Okay, so this is Weierstrass's continuous but nowhere differentiable function. And again, we have not gone through the proof that this is actually the derivative. Why?
Because we're physics right now?
No, but not a bad guess walking in. Because it's not the derivative, because the function is not differentiable. Right? You have to just technically prove that there is no derivative for this function. This is the natural candidate, and this candidate does not work. Right? So there's lots of proofs online. You know, if you're really interested, by all means, I strongly urge you to look at that, talk to me. I'm happy to discuss further. I just want you to get a sense of what can go wrong. And so just because I have a series that converges does not mean I can differentiate term by term. Okay, what I want to do now is talk a little bit about Laplace's method, or the method of stationary phase. How many of you have seen either one of these? And they're related. So nothing in the physics?
I haven't heard that word before.
So, trying to estimate the value of highly oscillatory integrals? Okay. So someday Professor Strauch and I want to teach a wrestling-inspired version of mathematical methods of physics, where we have real discussions in class about the right ways to look at things. And so the idea of stationary phase would be a wonderful thing to look at for at least a week or two. I mean, this is a huge topic. We're going to spend maybe half an hour on it. So, again, I apologize. This is a first course in complex. I am trying to show you what's out there and give you a sense of what's happening. So, along those lines, your homework for this week is in some sense optional. I will drop your lowest homework assignment of the semester. If you don't do this homework assignment, the final one, where I think it's choose 5 out of 7 problems, I'll just drop that and it won't affect your average. If you do it, then I will drop whichever one helps your average the most. It may not be whichever homework you had the lowest percentage on, because again, different homeworks have different weights. The problems that are due is basically a hodgepodge of results from the beginning of the semester to the method of stationary phase. So it's optional, you don't have to do it, but if you do it, I will then drop whatever homework is going to be most advantageous to you at other points in the semester. I will apply Laplace's method to try to estimate the value of n factorial. And so we'll actually use this to prove Stirling's formula rigorously. Okay? So it's a really nice application. For those of you who also want to try to get a sense of values of integrals, how many of you have seen Feynman's path integral approach to physics? Or heard about it? With the integral of the action? I think that's what it is. This is another way where we have these highly oscillatory things and only certain paths really contribute in the limit. And just trying to figure out what's going on. So here's the framework. So you have the integral from 0 to infinity of, well, let's do it e to the negative s phi of x c of x dx. Phi and c are infinitely differentiable. I'll assume s is real and positive. I'll look at s going to infinity. Okay, this should be plenty of reasonable stuff. And I want to try to understand what is happening for large values of s. Well, for large values of s, what do you expect to be happening? So I probably want to assume a little bit more about phi. Phi is the more important one because it's in the exponential. What do I want to assume about phi?
It's
Bounded, positive, right? If it's negative 5, that's really bad as s goes to infinity. So I want phi to be positive. And so what we'll assume is phi prime of x naught equals 0, a less than x naught less than b. So there's some point where phi prime vanishes in my interval ab, and I'll assume phi double prime of x is greater than 0. So what kind of point do I have? Local minimum. So I always have to draw the parabola, y equals x squared, the derivative is 2x, then the second derivative is 2. Okay, so the second derivative is positive, so I have a minimum. So I'm going to have a minimum. Okay? And then the theorem is that the integral is equal to C of x naught, and I just want to write it properly, times 2 pi divided by square root of v double prime of x naught e to the negative s v of x naught. I think I got everything correct. Times 1 over s to the half. So I've got a couple of terms coming into play here, and then my error term is going to be of size, I think 1 over s to the 3 halves, I'm writing it. 1 over s, well here, I'll write it like this, as 1 plus 1 over s. There's lots of different ways of writing it. So I'm trying to get main term and lower order term. So the main term will be this. The lower order term is going to be at least a 1 over s smaller. Well, if s is getting really large, a 1 over s smaller is quite significant. If you think about Stirling's formula, if you've seen Stirling's formula for the gamma function, Stirling says n factorial is approximately n to the n e to the minus n square root of 2 pi n times 1, and it's plus or minus, I always forget, 1 over 12n. So when n is very large, the error term is 1 over n times the main term. So when you see a formula like this, the first things you should be asking yourself is this reasonable? Does this have features that make sense? So there's a lot of stuff going on.
Yeah.
It's like, oh wait a minute, there's a square root over the 2 pi. Obviously. Does this have any features that look reasonable?
You mean which one?
This. Does that answer look reasonable? What, when you look at that expression, what terms say, yeah, I dig that, I can see that why that would be there. I'm writing in a slightly different order than in the book.
Well, you have the same term in integral that appear here. You're just adding in a bunch of stuff that's small.
What do you think the most important point for the integral is?
Where phi is smallest.
Where phi is smallest. Where's phi smallest?
At its minimum.
At its minimum, at x naught. So at its smallest, I get e to the negative s, phi of x naught, c of x naught. Oh, look, phi of x naught, e to the negative. There we go. That's where it's smallest. Then the question is essentially, how big of a range do I get for where it's smallest? And what this is telling me is that range is related to a 2 pi, a phi double prime of x naught, and the square root of s. That's a little bit harder to see. But it's a question of, for what scale, for what values, how big of a range of s can I take and see something like this? Alright, so let's try to do the proof. So we can write phi of x as phi double prime of x naught, x minus x naught squared over 2, times 1 plus little phi of x. Or I can even do it maybe x minus x naught, where phi of u is 1 plus some error of size u. So big O of u means some error that's at most a constant times u. Why is this true? Why do I have an expansion like this?
It's from Taylor series.
It's from Taylor series, right? So is this correct, or have I made a mistake?
Well, the first term is 0, so that term shouldn't be there.
Why is the first term 0?
Do we define it that way?
We did not. We have not. So what should we do?
Find the first term.
Define the first term to be 0. Because really, if the first term of phi is not 0, all I have to do is I just have to play, follow the notation. And if I don't have it 0, well look, I can subtract it and then add it back, and then I would pull out an e to the negative s phi of x naught. So, without loss of generality, phi of x naught equals 0. It's sufficient to consider that case. If it wasn't 0, I can just add 0 and deal with it. Yes?
Should be phi or phi prime to 0. Well, we have phi prime.
No, big phi. Right? Because I'm assuming the 0th order term in the Taylor series expansion is
Okay.
0. Now, if I shift it, does that change the value of the derivative at x naught? No. Fortunately, if I add a constant, I don't change the value of the derivative. So I can make this assumption. Okay. And now what happens is, well, the next term is going to be phi double prime x naught, x minus x naught squared over 2 factorial, and then the next term will be x minus x naught cubed over 3 factorial with a triple derivative, blah, 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 blah. And I'm assuming my function is infinitely differentiable. Technically, that might not be enough. I want some kind of Taylor series expansion that converges. I'm sorry?
Analytic.
Yeah, so maybe instead of saying infinitely differentiable, maybe I should say real analytic. Right? Is the camera still recording? Okay. I just heard a little beep. Oh, okay, that's just the voices in my head. Okay, so we will assume that it's real analytic. The question is, if it's infinitely differentiable, is that enough to get something like this? Well, again, I'm not saying that phi is given by a Taylor series expansion. I'm saying that there is some function phi that vanishes at 0. That's very different. And that I believe you can still show if phi and c are just infinitely differentiable. However, let's make life easy. Let's just assume they're real analytic. I'm not worried about trying to get things in the greatest possible generality. So now, if I look at this, what do I have? My exponential is e to the negative. Exponential is e to the negative s phi double prime of x naught, x minus x naught over 2 times 1 plus phi of x minus x naught. So again, the phi of x minus x naught doesn't really matter. That's going to be smaller and lower order. But what does this main thing look like? What does this exponential look like?
Gaussian.
It looks like a Gaussian, right? So let's let y be equal to x minus x naught times the square root of 1 minus phi of x minus x naught. There's a couple of different ways of doing the algebra. I want to make sure this is the same way as in my notes. Okay. I'm sorry. I don't need this 1 minus. Oh, I'm sorry. I don't want the plus 1 here. I'm sorry. I'm writing phi of u as 1 plus order of u. So if I'm writing it as 1 plus order of u, then it's already got that 1 that I need. So, you can do it 2 different ways. You can write it as 1 plus, or you can just write it as 0. I prefer to write things as 1 plus, but the book is just doing it as building in that 1 inside it. So I want my notation to match what the book is doing. So, sorry. So we will write it this way, as phi of x minus x naught square root. And again, phi of x is b double prime of x naught over 2 x minus x naught squared times times phi of x minus x naught. So I'm letting y be x minus x naught times that. If you do some calculus, you'll see dy dx at x equals x naught is equal to 1. Dx dy at the point x naught will be 1 plus some order of y. It's going to be small. This is basically just playing around with the Taylor series and inverting the functions. Phi starts off as 1, so when I expand things out, it's going to look like y is x minus x naught plus something like x minus x naught squared. So at a first order, dy equals dx. and the corrections are going to be lower order. And so dy dx at x equals x naught is 1, dx dy at x naught is 1, and then the error is going to look like some multiple of y. That's just essentially saying, look, these are essentially very close to each other. I don't have y equals x squared. I don't have y equals x cubed. I want to do this deliberately because it's a Gaussian. So I'm basically trying to follow the book as much as possible, but I don't want to use the argument from the earlier section in the book. I want to use arguments directly thank you, directly on the Gaussian. So if I have this as my change of variables, the exponential becomes e to the minus s phi double prime of x naught times y squared over 2. How should I write that? So for those of you who've taken probability with me, you're now in the hot seat. And I see at least 4 people. How should I write that?
Do we want to take the coefficients of the y squared and put them like 1 over the denominator?
Yes, why?
Because we want the sigma term, the variance term.
Right. I want to write that as e to the minus y squared over 2 sigma squared. When you write a Gaussian, that's how you write a Gaussian. Right? And so, so my sigma squared, it's basically 1 over s phi double prime of x naught. Therefore, sigma squared is 1 over s phi double prime of x naught. So sigma is 1 over s phi double prime of x naught square root. We now have a square root of s and a square root of phi double prime. 2 of the key things that came into our formula. We were trying to figure out over what range do we have to worry about integrating this function. This is telling us the range. Go a couple of standard deviations and you're fine. So again, we have an integral from a to b of e to the minus s phi of x c of x dx. And my point x naught is in the range from a to b. So when I change variables, it's like I'm integrating from alpha to beta. I've changed variables, and alpha will be less than 0, beta will be greater than 0. I'll have a e to the negative y squared over 2 sigma squared, with sigma as above. I have c of x. Well, now c of x has to be replaced with some function in terms of y. Right? So I'll call it c tilde of y. My variable has now been changed. But when x is very close to x naught, y is going to be very close to 0. Now I also have to remember I have a change of variable formula. Well, my dy dx is going to be 1 plus order of y. 1 plus a big O of y. So when I look at what's going on, c of y is basically going to be c of x naught plus some error of size y. And the reason is, alpha and beta are fixed, but I'm letting s go to infinity. If s goes to infinity, what happens to sigma? Sigma's going to 0. Let's think, what does it mean for sigma to be going to 0? I have something that looks like a Gaussian with essentially 0 variance. Okay. When you think of the dream integrals that I could potentially give you, I'm not going to give you the function that's identically 0. That's sadly not going to happen. But a Gaussian with really, really narrow, this sounds really good. What is it looking like?
Approximation of the
Approximation to an identity, a delta spike, what we saw when we were doing Fourier analysis. Right? So this is just an approximation, but as we get better and better and better, the error becomes insignificant. And again, to move a fixed distance on the x scale, a fixed distance on the y scale, boy, this is going to be so small, it's not going to really matter. Because again, a and b are fixed, alpha and beta are fixed. S is getting so small that if I move just a few standard deviations away, this has been cranked down to nothing. And so really I only care about this approximation when y is very close to 0. If y is starting to get sizably away from 0, it doesn't matter. So again, you can do a little bit more careful analysis of what's going on, but really an approximation like this is more than enough. Now, not surprisingly, the better approximations you do, the more information you'll get about the expansion. You can start to actually sniff out the secondary term, the tertiary term. If I want just the main term, I say screw this. You know, c of x naught plus small. Who cares about plus small? Right? So now, it's approximately the integral from minus infinity to infinity of e to the negative y squared over 2 sigma squared. I'll pull out the c of x naught. dy plus some error of approximately this shape. E to the minus y squared over 2 sigma squared, absolute value of y dy.
Where do we get that here?
Well, I basically have an
I see. So
an order of y.
Now, since we're approximating phi with a function that's of order y, wouldn't our error term have an order y squared?
Over here?
Yeah, multiply, because if we're multiplying two order y terms, we're getting something.
But no, the domination here is not by the 1.
Oh, I see.
Right? So order of y times 1 is order of y. Order of y times order of y is order of y squared.
Right.
And order of y squared will be small.
Oh, got it.
So now, what does this integral equal?
1 times it normalizing.
1 times the normalizing constant. What's the normalizing constant?
Something like that.
Yes. Right? So I want to multiply this by 1 over square root of 2 pi sigma squared. Since if I do that, then I have to multiply by square root of 2 pi sigma squared. So this is equal to c of x naught square root of 2 pi sigma squared. Well, sigma squared is just 1 over this. And so when I have a square root of sigma squared, that just becomes a sigma. And so then I'll have a s to the 1/2 square root of phi double prime of x naught. Right? Because I had to multiply by the square root of 2 pi sigma squared. The square root of sigma squared is sigma. Sigma is 1 over square root of s phi double prime of x naught. Yes?
Why do we multiply by 2 pi sigma squared?
Because if I have a Gaussian, the integral of a Gaussian is 1 if it has the right normalization factor. So we talked about this last time, that the integral of 1 over 2 pi sigma squared square root e to the negative x squared over 2 sigma squared dx equals 1. That was the fact we were using. And so I don't have that 1 over square root of 2 pi sigma squared. So the value of this integral is just the square root of 2 pi sigma squared. One way we saw this was we used this polar trick. We actually squared the integral and then said we have e to the minus x squared, we have e to the minus y squared. We combined it, we got an e to the minus r squared. dx dy became r dr d theta. We jumped for joy, at least in our minds, that yay, the r dr d theta, beautiful. We have e to the minus r squared, r dr integrates perfectly. You could also, if you really understand the gamma function, you could interpret this in terms of a special value of a gamma function. This is gamma of a half. But the point is, it's the integral of a Gaussian. We know the answer for the integral of a Gaussian. And so once we have that, we have the main term. Now we have the secondary term. So what's the difference between the secondary term and the main term? Yeah, so basically all I have to do is find the mean of the absolute value of a normal random variable. Well, this is the same as integrating from 0 to infinity of the absolute value of y. And I'll leave this as an exercise. it's not too bad to do it directly. Why? Well, we have e to the minus y squared and we have a y dy. Right? You know, life is good.
Go from 0
Go from 0 to infinity and double. And of course, it doesn't even matter if we double. And what you'll see when you do this is you get that this integral is essentially on the order of 1 over sigma. Or actually here, it's going to be, I think, on the order of 1 over sigma squared now. We first get a 1 over, it's going to be on the order of sigma squared, not 1 over sigma squared. We get 1 sigma because the integral of this was just the square root of 2 pi sigma squared. But now y is approximately at most sigma. So this is going to look like a sigma squared. And that's going to give us an extra power of s. So I'll let you, do the details here in terms of the lower order corrections you get. And so you can figure out exactly what it is, and it comes out that the next power will be a 1 over s, small. Right? I just want to do enough to give you an understanding of the shape of how these calculations are done. Plus smaller by integration. Okay. This is the method of stationary phase. Okay. So to recap, we said, well, look, we might as well assume your big phi of x naught is 0, because if it's not, we can just pull out its behavior. And then because we're assuming phi double prime is positive in the region, we have a local min. Well, when s gets really, really large, since this is local min, as I move away from the local min, this is going to be cranked down to 0 extremely rapidly, because s is huge. Any small difference between phi of x naught and phi of x1 is going to be magnified enormously by large values of s. So essentially, all the contribution comes from x very close to x naught. And then it all comes down to, what do we mean by close? Close has to depend on what? So for this problem, what does close have to depend on? What things in the problem will close depend on? S, right? Because when we're measuring things, well, let's see. If I'm moving like 1 over s to the 50,000, if I'm moving 1 over s to the 50,000, I've essentially not moved. If I move 1 over s to the 1/4, I probably have moved when I multiply by s. So the notion of how much I can move is going to be a function of s. And it should also depend on the second derivative at x naught, because that's going to just tell me my local scaling factor. So this is the method of stationary phase. Okay? The question, of course, is there ever an example that meets all of these restrictions? So if everybody's copied this, I'll leave the statement of the theorem on the board and erase the left-hand side. Has everybody copied this? Okay. And so, the input we needed at the very end was we needed to know the Gaussian. Well, fortunately we know the Gaussian, so all is good. Alright, so what I want to do now is I want to do Stirling. So, gamma of s is the integral from 0 to infinity of x to the s e to the minus x dx over x. I could have written it as x to the s minus 1. This way, I think, just does the algebra a little bit nicer. So I need to figure out what is phi, what is c. Do you have a candidate for either? I'm sorry? I need a candidate for phi or for c.
The
Sounds like 2 words. First word, oscillatory.
one that looks like I. To be log.
Phi or c? Which one do you want?
The upper one, in the exponent.
Okay, what should phi be?
Negative log x.
So phi of x should be negative log x.
Oh wait, there's an x one. Oh wait, yeah, that's okay.
So how are you getting that?
Set x to the s equals e to the negative s.
Well, if it's x to the s becomes e to the s log x. So you're trying to convert the x to the s into an exponential.
Yeah.
Alright, so if we do that,
Oh.
we would get the integral from 0 to infinity e to the negative, e to the s log x minus x dx over x.
Oh.
And so what would phi of x be? So you want a minus sign, so we can write it as minus s times minus log x. And then we're fine. The problem is if we do that, phi of x is minus log x. What's phi prime of x?
Negative 1 over x.
Negative 1 over x. Phi double prime of x is 1 over x squared. Hey, that's always greater than 0 in the region we care about. That's good. What's bad?
We don't have 0.
It doesn't have a 0. Okay, this is the most natural thing to try, but it doesn't have a 0. If we did this, we would have c of x be e to the minus x times 1 over x. Unfortunately, this doesn't work because our function phi doesn't satisfy the requirements. I don't care that it's not 0 at 0. I can always fix that. It's not 0 at 1 or whatever. I can always fix that if I have a point where phi prime vanishes. I don't have a point where phi prime vanishes. So what this tells us is this can't be the correct definition. The problem is, it looks like there's nothing else we can do. Right? Because the problem is, well, that's the only place I have s. I can't switch the order of integration. Why? Why can't I switch the order of integration?
What order?
Exactly. Yes. There is no order of integration to switch. I could at least take logarithms, so I mean, at least have something that I can do. I have to change variables. That's the only thing that's left. And this is why I wanted to write it as dx over x, to emphasize the change of variables. If I rescale x by 5, does dx over x change? No. What should I change variables by? S. Why?
It's the only other variable.
It's the only other thing in play, right? There's nothing else I can do. I've got to get an S somehow, right? So, cross your fingers, whatever you do for luck, hope that somehow x to sx helps. And now we would get the integral from 0 to infinity of what? I'll write this first as 0 to infinity e to the s log x minus x dx over x. So now when I replace x with sx, I'll get e to the s log sx minus sx dx over x. What can I do? What should I do now?
Separate out. Well, it doesn't yet look like that form, so we
Yes.
should separate it out since we have like an extra sx there.
Okay, so what should I do?
So it should be maybe e to the negative sx times, or no, actually, that won't work.
So what algebra simplification can I do?
Like a product is a sum of the log.
Yeah, so this is going to be e to the s log s plus e to the s log x. Ooh, an s log s. There's no x dependence. Let's pull that outside the integral. E to the s log s. And if you think that s is going to be n, this will be e to the n log n. That's going to be n to the n. Now I have the integral from 0 to infinity, and now I'll have e
Wait.
to...
Where did the x go? Like, why can we...
Because
Give it log of
log of
s.
sx is log s plus log x. So I take
Oh,
the
that's
s log
true.
s out. And now I have e to the s log s minus, so I'll have minus s times x minus log of x dx over x. Okay. Does that look good?
It's better.
Looks much better, right?
Well, now we have a natural candidate for phi, and
Yeah, so what should we try for phi?
for phi, everything that's not s in the encoded,
And c,
1 over x.
both nice functions. What's phi prime of x?
1 minus 1 over x.
Does that have a 0? Yes. How many zeros does it have? Good. We don't know what to do if we have multiple zeros. What about phi double prime?
Exactly what we have before 1 over x squared.
Yeah, it'll just be 1 over x squared. And there we go. And now we just quote the result. And now you get Stirling's formula. Now, we could play with a little bit. You know, phi of 1 is not equal to 0. What is phi of 1 equal? 1. So if I wanted to, I could subtract 1 and then add 1. Right? If I subtract 1 and add 1, I'll get an e to the minus s coming out. And so I want to do that just because I think you'll like what happens. So we get e to the s log s minus s, 0 to infinity, e to the negative s, x minus log of x minus 1 dx over x. And now, if I take phi of x to be x minus log x minus 1, phi of 1 is 0, phi prime of 1 is 0, phi double prime is greater than 0. And if I take s equals n, I get I get e to the n log n minus n. E to the n log n is e to the log n to the n. This is just n to the n, e to the minus n, which looks a lot like the beginning of Stirling. What comes next is the square root of 2 pi n. And that's what you're going to get from the rest.
Are we still worried about the fact that...
Nope.
Okay. When we took the derivative, we still ended up with a 1 over x.
That's fine.
Okay. Because it's still not going to work at 0.
It's not going to work at 0. But as we get very close to 0, the x to the s term is going to become negligible.
True.
And so we'll be fine.
Okay.
And because we'll have a small number to an enormous power. So the contribution, so if I want to, I can actually start the integral at 1/2 if I'd like. Right? There's really not going to be much to work. Now, of course, the other thing is, when you say x close to 0, x close to 1, you don't really mean here. You mean down here, after we've done the change of variables.
Oh, I see. Okay, yeah.
And so when you say x is really close to 1, or x is really close to 0, really, you're starting very far away from 0 in this integral. If x was equal to 1/2, that translates to s over 2. Alright, so this is the method of stationary phase. Stationary phase is really a special case where s is chosen to be, I think, pure imaginary. And this gives you highly oscillatory integrals. And it essentially says most of the contribution comes from the place where the derivative is 0, because then the phase is all aligned. If the derivative is not 0, then you have this rapidly oscillating phase. And if you're integrating something with a rapidly oscillating phase, it essentially doesn't contribute. And so, just briefly, and again, this is for the physicists, or the physicists at heart, if I have something e to the minus I s, phi of x, c of x, well, I've got my sines and my cosines, and this is going to be highly oscillatory. So, it's going to look something like this. And if I integrate a nice function, against this, I've got I've got positive regions, negative regions, they're going to essentially cancel each other out. And so I would expect most of these integrals to essentially be 0, because the oscillation is just so large that, c doesn't really change that much. And so in a short interval, my sines and cosines, sine goes like this, generally cosine goes like this, but we've now compactified them into such a small interval that c doesn't have enough time to change before I go from a positive weight to a negative weight, and things will cancel out. And so I expect integrals like this in general to be very small. The exception is if I happen to be at a point where phi prime is 0. And then if phi prime is 0, then essentially I have a region where the phase is constant. And if the phase is constant, I'm no longer getting oscillation and getting cancellation. And so if you've seen the Feynman integrals, this is a situation where you might see something along these lines. Okay. Any questions on this? We have 2 minutes. Do you want to see a proof of the Riemann hypothesis?
Yeah.
Oh, sure.
2 minutes should be more than enough time. So zeta of s is the product over p of 1 minus 1 over p to the s inverse. And this is okay if the real part of s is greater than 1, and we have an analytic continuation. Do not write this down. Do not watch this video and think that this is serious. Maybe I should even turn off. I won't turn off the video. I'll leave it on. I do not believe this is correct. I do not believe this is salvageable. The Riemann zeta function has an analytic continuation. What if I take zeta of s and I replace it with 1 minus 1 over 2 to the s inverse over, 2s. 1 minus 1 over 2 to the s. How do I do this? I want to do it this way. So I multiply by this factor. 1 minus 1 over 2 to the 2s, inverse over 1 minus 1 over 2 to the s inverse. This is going to cancel the p equals 2 factor, right? And replace the p equals 2 with 1 over 2 to the 2s. Is this factor ever 0? No. So then I'll just do times zeta of s. So the only, if I take s to be at least a half, 2 to the 2 times 1/2, that's 2 to the first power. That's not enough to have this be 0. This is not going to be 0, it's not going to have any new poles. I haven't introduced any zeros or any poles. Does this function have the same zeros as the zeta function? Yes or no? Yeah. So I will call that function zeta of 2. I will define zeta of 3 of s to be 1 minus 1 over 3 to the 2s over 1 minus 1 over 3 to the s inverse times zeta of 2 of s. Is this going to introduce any zeros or poles? I continue this process, and I work where the real part of s is greater than 1. I'll get some function zeta infinity of s. Everything is fine because I'm in a region where everything converges. But each one of these has an analytic continuation. Is this hard to analytically continue this factor? No, it's a ratio of 2 numbers. And we know the analytic continuation of zeta. So I have an analytic continuation for my new function. But, can somebody tell me briefly, what does this function equal? So I just keep going through and I replace every prime with a prime squared. It's just the product over p, 1 minus 1 over p to the 2s inverse. What function is that? Zeta of
2s.
Zeta of 2s. Well, I know the zeta function has no zeros if the real part of s is greater than 1. So zeta of 2s will have no zeros if the real part of s is greater than a half. I have just shown that the Riemann hypothesis is true. Yes. So if you can fix this up, there's $1 million. As I said, I will let you keep 95% of it. That's much better than the government will give you. What is wrong with this argument? Everything uniformly converges. In the limit, I get zeta of 2s.
Is there something wrong with the way you take the limit?
Yes.
As you extend it to infinity, something goes skewed.
So I will let you think about this for next time. there is something wrong here. Right? In a completely unsalvageable way. I have done a physical